in equilibrium. When everything is in equilibrium, that means the forces in the x and y directions are equal. So if you're looking at a system like this, what is pulling the system down? What is pulling the system down? Mass, right? So the mass that you have, or the weight of this object that you have, yeah, it should only point on that. I only want that. Now, this is just, yeah. This part is, that will be fine. Yeah. Thanks. So that means that if you have a force, which is in this case W, the weight, is equal to the part that is related to T1 projected in that direction. So basically, let's say this part. And then T2, which is this. So in this case, TW is equal to T1, whatever that angle is. So let's call that angle alpha, right? And then whatever that angle is, beta. So if I want projecting T1 onto that angle, how do I do it? By using T1 times cos of alpha, right? The projection on that y plus T2 cos of beta. In the equation that I did last time, T1 and T2 were equal, so we didn't worry about it. Why? Very simple, because alpha and beta were simply 45 degrees. They were the same. So it turns out to be equal. But if they're not equal, then they would have a different value. So you really end up with two equations. Two equations, and from that equation you're supposed to find T1 and T2. In the example we did in the class, one equation was already known. And what was that? That T1 was equal to T2 because of that 45 degree. You follow? But in other examples that you have in your book, they're not equal. So what? So the relationship between T1 and T2 is based on the angles that they make. Because, by the way, if I am looking at these forces in the x direction, the components that they have in the x directions are these. Does W have any component in the x direction? No. So again, looking at the equilibrium, what we are saying here is that these components should be equal to one another. So in other words, in this case, what you're saying is T2 sine of 90 or pi over 2 minus beta is equal to T1 sine of pi over 2 minus alpha. Basically, we're looking at their projection on the x-axis. Before, these two angles were the same. What were they? 45 degrees. So the sines on both sides were simply sine of 45 degrees. Right? If they were sine of 45 degrees, they would just cancel out. So that was your original equation, with that T1 was equal to T2. Right? In this case, if they're not equal, this is the relationship. So from this relationship, you find T2, and you put it in the other equation, and you find T1. Does that make sense? Come on, raise your hand. It doesn't matter. I mean, we're not doing statics here. This is pure geometry. Pure. Nothing else. Pure logic. Has nothing to do with you understanding forces, understanding dynamics, or none of that. It's very simple. When do we get the situation like this? That something is hung, but tension in one cable is, yeah.
Double crane setup?
Yeah, exactly. You have a crane like this, right? So if one cable is shorter than the other one, then naturally something happens with regards to the forces. And that's what we're getting over there. Okay? Logic. So I also have received some questions, I don't know why, but again about, where my recitation is and, situations like that. Let's say what's it? Blackboard, right? Let's put it at 50%. So on your Blackboard, you all have access to this, right? And I keep telling you that you really need to check it out. Now you see a lot of posting here. How many of you have seen these postings there? Right, not all of you. You need to do that because almost every day we put something in there. So for example here, you said all of them were posted on September 16, but you will see some dates. So let's say, for example, this one. What is this? That's right. There's a reason that thing is there. So if you miss something, you want to refresh your memory, is right there. Okay? That's why we have that thing over there. Okay? Any questions? Yeah, sound terrible, right? So you look at lab locations. So here it says week 4, room 312. What week are we in? Huh? 4. So this week, where are you going to go? There you are. So what else? Come down. Recitations. Recitation update. Now this update was done in August 26. We could have an update today. I don't know if we are, but that means you need to constantly go there and find it. And pretty soon I'm going to start posting the homework grades that you get. You're going to get your homeworks back this week. I'm going to maybe put some exercises there for you with in preparation for your quiz. All kinds of announcements. So try to really familiarize yourself with this Blackboard. And any questions that you might have should be normally answered here. So as part of mine, let's go to, what is this? So you notice that, for example, I have an online attendance that actually I forgot to bring a page, so maybe one of you can circulate the page for today's class list, but it will give you some idea. Let's pull that out. I don't know if you have access to this, but I'm going to post it to you so you know where you stand. So you will see, for example, all of your names, and in front of it I have P as present and A, for some people, an absent. All right? So I have all of your attendances there. This is going to assist me in setting up your grades later on. Okay? Every day that I collect these, the information is going to go there. Any questions so far? So this is really an idea what why I'm using the Blackboard. Eventually, we're also going to look at some assessment exercises there. All right, let's get this out, and now. I don't know where that is. On or let's see. Okay. All right, so today we're going to be talking about complex numbers. All right? How many of you know what a complex number is? Go on.
It's any ordinary number multiplied by an imaginary number, an imaginary number being the square root of a negative number.
Right. Do you agree? Complex number, I mean, this is really going into detail. So when I tell you something is complex, what am I trying to tell you? It's not easy to understand. Right? It's complex. It's not easy to understand. And the reason that we do this, and that's what I want to talk about today, why do we have complex numbers in engineering? What have you done so far in our class? What have we done? If we wanted to really explain it to somebody else, what have we done so far in all the 3 weeks that we've been together? Come on, explain to me. What have we done? Yeah. Right. What these equations and different concepts in math, what have we used it for? Yes. Right, to describe real-world problems. To describe real-world problems. So when we talk about the position vector or a position, that means we are using mathematics as a means of describing the physical shape. So we have learned about linear algebra, okay? A line, formula of a line. The formula of a line showed us the movement of something in a linear fashion. So we use math to describe a physical system. Then we went into a quadratic form, where I said, okay, not everything moves in a line. Some things actually moves on a curve. The simplest form of a curve is a quadratic form. Then we went from there to what? To vectors. Where we said, in physical systems, not only you have a magnitude, but you also have a direction. Or in other words, not only you have a value, but you have a purpose. Okay? So when you have a direction, so if I tell you, why are you here? What do you say? Because my parents made me to? Why are you here? I'm here to get education. That's the scalar quantity, right? But I'm getting this education so I can get a job. Do you see? A direction, a purpose. That's the vector. So we described the vector. The simplest form was in the Cartesian coordinate system, right? Or rectangular system. How do we describe the vector? By using,
Direction and magnitude.
right? And the direction was described by what? Yeah. Right? I and j. Right? Unit vectors. What else did we learn? The same vector. What else we use to describe it? Angle and magnitude. What do we call that? Polar form. You remember polar form? It had a magnitude and an angle. So now we're going into a different format, a complex number. A complex number is, the intention is exactly the same thing as the others. To describe the physical system, but now in a more engineering terminology. So, and there's a reason for that. So one of you said a complex number, say z, has real and imaginary parts. A real and imaginary. So if somebody tells you it has a real and imaginary, what does the imaginary tell you? That it doesn't exist? That you're imagining it? That's what it means, right? Imaginary. You're imagining things. But what we're telling you is that this real and imaginary that we're talking about, it is going to assist you in describing a physical system. Right? But when you deal with engineering systems, it's always important for you to describe the relative, connection to one another. Where you say, for example, this is the voltage and the current has a 90-degree phase angle. You know, in circuits. You'll know that. And that's where the imaginary part is going to come into play. So when we talk about a complex number that has both real and imaginary, then we can describe it in this format. Now, how many of you have seen this? Come on, raise your hand. Can one of you who've seen this tell me where you saw this? Yeah. Algebra 2. Did any of you see it in physics? Must have seen it maybe in the electrical circuits if you did any of that. But in Algebra 2 you saw this. A plus BI. Now, you know, again, engineers are kind of neurotic. We're kind of, we have certain resistances to certain things. And then the issue is that we really don't like to use I. Why don't we use I? Yeah. All right. What else?
Because I is the symbol for electrical current, so you want to use a different letter like J.
That's right. So you see, we have a very limited brain function, engineers. You'll get to that point. I don't want to get confused. When I use I, majority of us think immediately of current. Whether you are a mechanical, electrical, civil, biochemical, you name it. The moment we say I, to me means current. Well, somebody said, well, when you use I and J in X and Y, to be perfectly honest, we don't. What we showed you, the I and J, was what mathematicians use. What we use is right here, a complex number. Because our thinking is directly linked to a physical system. And a physical system is much easier described in this format and other formats that I'm going to show you than what we have seen so far. So to simplify it for ourselves, we use it as he said it, A plus BJ. Is there a difference between this I and J and the I and J that we use for vector representations? Do you remember that? Yeah.
These ones don't have the hat.
That's right. They don't have the hat. What did the hat do? What was that? No, the I and J that we had with the hat. You remember the I hat and J hat? What did that describe? Why did we put that hat on? Yeah, well, we symbolized directions. Those describes directions. What this does not describe direction per se. It's really showing a complex number. So they are exactly the same. We want to even be more neurotic than this, because we, in fact, like to show it this way. Is there a difference between A plus BJ or A plus JB? No. There is no difference. They are exactly the same. Especially when we say they are exactly the same, sometimes we show it this way. Have you seen this? 3 bars. In engineering, when we say something, I is equal to J, it's very different than when I say I and J. Well, if I could write, I and J are exactly the same. So if they're French, if I is French, J is French too. Okay? There's a difference between the two. So instead of say, me and you are 5 foot, say 6 inches, there's a difference that we and you are identical twins. Do you see the difference? We are exactly the same. And that's the terminology of 3 bars. So in this case, I and J are exactly the same. So all these 3 that you see are basically identical. 3 ways that we are describing a complex number. So far so good. But what is J? Now somebody said that I and J are basically square root of minus 1. How on earth can we have a square root of minus 1? You've been told ever since, I guess, you knew about mathematics, that you cannot take a square root of a negative number, right? But then what is it? Square root of minus 1. Yes? Right, but why? Why do we call it that way? Yeah, it's not real. So the only way that we could have made something up was to use a terminology that really confuses us. But here's the thing. This terminology is really going to help us when it comes to vector manipulations. So far, you've seen how a position of an object can be described by using I and J, right? But if I tell you, okay, that is a vector, but I want to multiply this vector by another vector. Now, how can we do this? How can I use the polar form or a vector form to do that multiplication? If I multiply I and J, in other words, if I look at I squared or J squared, what do I get? Negative 1. Right? So in the angular term, what does negative 1 describe? What cosine of an angle is negative 1? Yeah. Cosine of 180. Right? So when I say minus 1, you're multiplying something and it gives you a minus 1. I'm kind of taking you 3 years away from where you are right now. Then you can relate that to an angle between 2 vectors. So if I wanted to show that this gentleman and me have a 180-degree phase angle, okay, we're going in the opposite direction. That could have easily been described by using a vector manipulation that would give me an I times J of is equal to minus 1. And then when later on you start multiplying, subtracting these vectors with one another, you'll see how useful this is going to be. Questions so far? All right, so this is an imaginary number. Basically means that if I have a complex number, then there's got to be a real part to this complex number. In this case, my real part is A. And what is the imaginary part? What is the imaginary part? It's B. So B represents the imaginary part. What makes B imaginary is what? J, right? J. So in fact, both A and B are like components of Z. So if A and B are like components of Z, then we can say that Z is equal to A plus BI is analogous to a two-dimensional vector. So it's describing a two-dimensional vector for me. All right. Hopefully I've confused you enough. So the time has come to do an example. So, a one-link robot, I think you're beginning to get sick of this thing, right? Again, the same thing, a one-link robot that we have, and we want to look at the position of that one-link robot. So far, we have learned so many things. And if I want to describe the position of the tip of that one-link robot using px and py, the knowledge that we have, if I want to show it in the I and j, how would I describe the position? Position P bar. What does that equal to? Come on, somebody take a crack at it. Using px and py, what is the position of P? Somebody at the back. Come on, take a crack at it. No one's going to laugh at you. Go on. I'm going to use px and py using I and j coordinates. How do you describe it? Well, I want to see somebody in the back. Come on, raise your hand. It's okay. It's okay to make mistakes. Go ahead. I'm going to pick. Somebody's going to volunteer and be the hero. 365 on your t-shirt. What's your name? Go on, take a crack at it. I want to use px and py using the I and j unit to describe the position of that. What do you say? P is equal to? I times j? You remember I and j were your unit vectors in the x and y direction. Yes? That's right, exactly it. That's it. Pxi. So, that was the rectangular system or the Cartesian system. In the polar form, if I want to describe that, how do I do it? Somebody. Yes? All right, so that will give you the magnitude P. Magnitude P. And the angle. That's right. That's the angle. So basically, in a polar form, all we do is using the magnitude and the little angle. Okay? So now I want to use it in a rectangular format based on the complex form. So if you notice, on the y-axis, I have defined it as an imaginary axis. So from now on, when we are dealing with complex numbers, the y-axis is our imaginary axis. And the real axis is the x-axis, right there. So using the complex format, the complex terminology, I am describing the tip of that one-link robot, P, as px plus pyj. This is a rectangular form of describing the vector, where before was pxi plus pyj. Right? So if I'm asking you what is the real part of that complex number, what do you say? Yes. Px, right. And the imaginary part? Right. So if I want to find out what px is, looking at this geometry, if I want to find out what px is, how do you find it? What is px? Yes. Well, no, don't look at that formula. I'm saying look at this. Tell me what is px based on the magnitude of that vector, which is p or L. What is px equal to? Yes. P cosine of theta. So basically, I can show that the real part of that vector is equal to px, which is the magnitude of the vector, which is p, times cosine of theta. So the next thing is, okay, now you found the real part. What about the imaginary part? What is the imaginary part of this vector? Yes. Py, which is equal to? P sine theta, right. And don't forget that the magnitude of P, which in this case is L, is the square root of px squared plus py squared. Does that look familiar to you? Where did we see this before? Where did you see this? Didn't we see it in the polar? Same thing. Okay? So, going back to the problem that we have, basically what we have done, we have used a polar form to describe a complex number. In this case, somebody told me what theta is. What was theta? What was theta? A tan 2 py over px. So using that concept, using the polar format, now what we want to do is we want to describe it in an exponential form now. Oh my God, you're using so many different terms. Yes?
So when you say 18 is that just the inverse of 10?
No. Well, yeah, I mean, it's the inverse of tan, yes. It's tan minus 1, exactly. The only difference is that A tan 2 also takes into consideration the quadrants. where the angle is, because tan minus 1 only gives you the angle from minus 90 to 90, where in this case we have 4 quadrants. That's why I said if you have a calculator that has a ray tan 2 is going to give you an angle, say 270 degrees. But using tan minus 1, you're not going to get 270. Okay? So it's exactly the same. You're right. All right, so now we want to show it in an exponential form. So in other words, if you have your complex number, which right now is written this way, you already know that P can be described this way. Or simply speaking, we can describe it this way. How did we get this? How did I get this from that? Can somebody tell me? First of all, do you agree with this? First line. Based on the geometry, right? We have up there. Px is simply the magnitude of P, or L in this case, times cosine of theta. So, how did I get this? What did I do? Yeah. Yeah, which we call it factorization. We factorize magnitude P. We factorize P, and that's what we have. Do you follow that? Do you agree? Very simple. It's just simple mathematics. So what we have here, inside the bracket, cos of theta plus j sine of theta is e to the power j theta. And this is called Euler's formula. Have you seen this before? Have you ever seen the terminology E? There's a value to it, but we don't want to get into that. So now we want to simplify this by assuming that cos of theta plus j sine of theta is simply equal to a j theta. Those of you who have seen E before, where did you see the E? Logs, right. Logs, because we have two kinds of logs. Natural logs, Neperian logs, E, and the other one was log of 10, right? So we saw it in those of you that might have done logarithms, we've seen it this. But at this moment, you don't need to go there. Just simply believe me that this is equal to a j theta. And the reason that we do this, because this formula, Euler's formula, is going to assist us when we do vector manipulations, like multiplications, like additions. Think about it. There are many ways that we can describe a position of a vector so far. But the one that we are really, really interested in is the exponential format of these two. So basically, now we can describe P in exponential form as the magnitude of P times e j theta, which is exactly the same as what we have up here. Exactly the same. Questions so far? So, going back to what we have again, if I want to summarize it, I can simply say that the position of the tip of a one-link robot can be described as a vector or a complex number. If I want to describe it as a vector, what do I say? P is equal to, come on, you gave me, yeah. Py, j, right. Don't forget the hats, right? So we can describe, first of all, in vector form, like this. You've seen it already. You don't forget the hats on the I and j, and the arrow above p, which means that's a vector. If I want to describe it in a complex form, in a rectangular manner, in a rectangular complex form, what do I say? Come on, yeah. Don't go to polar. No, we're not there yet. I said rectangular. When you say rectangular, that means you are using px and py. Rectangular using the sides, yes. Absolutely correct. When you see that, I'll put the j before py. And I want you to get used to it. The reason that we put j before it is for you to immediately identify the second term as an imaginary term. So, if I want to use it as a complex number and show it in a polar form, what do I do in a polar form? Polar form? Yes. Right, magnitude of P, angle theta. Which is the same as absolute, but a lot of people do not know absolute numbers. And then finally, we want to use it in an exponential form. What would that be? What was the exponential form? Yes? There you go. So the same vector is now shown in 4 different ways. So let's say that if I have vector 1 and vector 2, and they're both described in any of these, which one of them do you think is easier to multiply? Yes. That's right, the last one. Because if I describe, say, P1, if I describe, hopefully this is going to write. If I describe, I bring my own pen from now on. If I describe P1 as using the same thing as P1 times A j theta 1 and P2 as, say, P2 A j theta 2, it is much easier to use it this way than any one of them. It will just simply it's simplified. Because what is E j theta 1 times E j theta 2? What is that equal to? Right? Right? Somebody say j squared. Why? e to the power 2 times e to the power 3. Is that e to the power 6? Is equal to e to the power 2 plus 3, right? So if I have j theta 1 plus j theta 2 is simply j theta 1 plus theta 2, right? Not j squared. Follow? So mathematical manipulation is much easier if I use it in an exponential format. Time for an example. Impedance of an inductor. What is an inductor? First of all, what is impedance? So impedance means? Yeah. Huh? No. English language. Impede. When I'm impeded upon you, what am I saying? Huh? Slowing you down, right? I'm impeding, slowing. Do you know another words that might mean the same thing? Resist, right? You impede, you resist. Come on, you all took SAT, right? Vocab. So when we are saying impedance, we are effectively saying resistance. But resistance comes in different forms. So an inductor simply is a coil. A coil. Have you seen coils? In circuits, you will see that. Coils. And the reason we show it, because coils could also have something in there that would create a magnetic field. But impedance of an inductor is simply a resistance. So rather than using R from, what we do for an impedance, we use a new different term called Z, which is J omega L. That's not W. That's a you have letters, Greek letters. One is lowercase, uppercase. Omega is the lowercase of what you know as a uppercase of omega. So impedance of an inductor is written this way. So what do you think the units of that Z would be? Ohms, right, exactly. So from now on, we're using resistance or impedance as Z. And in this case, omega is simply the angular velocity of the current. Now, the current could be two different forms. One is direct current, the other one is alternating current. Do you know the difference? What is an example of a direct current? No, an example of a DC current. A DC current, yeah. Yeah, but just give me an example. Something. Batteries, right. Batteries give you DC, right? An alternating current, it kind of goes up and down. What is an example of that?
The lights.
Well, just put your finger in that outlet. You not only you'll know it, you feel it. That's an alternating current. So the alternating current has a frequency, omega, and that's where that omega is. So really, in this case, the omega is 2 pi f, which is frequency 60 hertz. What does hertz means? Hertz. Hertz. Have you heard that? Cycle per second. 60 cycles per second. Now, that outlet there has 60 hertz. Now, if you go to European countries, has a different frequencies there. In fact, they have different voltages there. So in this case, omega is 2 pi f. And the reason for that is that when you are getting an angle of, say, 45 degrees, 45 degree is a made-up number, where a physical number is the pi, which is really 2 pi is the circumference of one cycle. So you really want the angles to be in radians. In this case, the L, or the inductance, is measured in a new value called H. H stands for, have you seen that number? H is Henry's, against someone's name. You know, electrical engineers are really too proud of themselves. So they just named everything after themselves. Where it came from, I don't know, but it's Henry's. So in this case, if I want to find out the Z of this system, all I have to do is replace for the values of omega and L. What is the unit? What is the unit of Z? Huh? No, we said it before. What is the unit of Z? Impedance of an inductor. Impedance was the same as resistance, right? Ohm, right. Or simply speaking, Z is J 9.426 omega, or ohm, where Z is a complex number. And the reason that yes.
What was the point of having complex numbers?
Okay, so that's a very good question. Because, for example, if the current flows into this system, what it's telling you is there's a 90-degree phase difference between this and the direction of current. It's very much like when you're taking acceleration. So it has a physical meaning that when we are describing it in this case, because we are talking about the phase angle. I mean, phase angle, you're not familiar with that. But what we are telling you is that the inductance in an electrical system is a complex number. That's why it is important for you in math to understand the complex number. We don't want to get to the physics of this, because I'm giving you all the answers. But what I'm telling you, there is a direct application when you get to electricity and when you get to circuits to really bring the knowledge of complex numbers into practice. Do you follow what I'm saying? See, so far, I mean, the whole objective of this class is to show that the math that you're learning has a direct application into one of the subjects that you are going to see later on. And the simplest form is the circuits that almost every single one of you is going to take a course in engineering. So now when you're learning complex number in your math course, you just don't say, well, I never use this again. Here it is, right in front of you. All right. Any questions? All right. So where do we go for our lab this week? All right, good.